Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, thank you all for coming. I'd like to introduce Raluca Popa, who is concluding her internship here after concluding a very successful undergraduate period at MIT, during which she published multiple papers at prestigious conferences. So we anticipate a very successful career ahead of her, starting with this work she's done with us on cloud computing.
Hello everyone, I'm Raluca, and this is my end of internship talk. Too bad it's ending. So I will talk about enhancing cloud SLAs with security and designing a secure and practical cloud storage system. So this is work with Helen Wang, Jay Lorch, David Wolnar, and Li Zhang. So cloud technology is emerging rapidly, and more users are using it. The reason is that it provides more resources, such as more storage, also more computation power. It's also more reliable in the sense that the cloud can provide replication for you, and more available because the cloud is available from different parts of the world as long as you have connection to the internet. Also, it tends to be inexpensive, and it's much easier to buy cloud compute powers than have your own personal cluster. So there are various use cases for the cloud, and that's personal storage, in which a user can store his personal file system on the cloud and thus benefit from the reliability the cloud provides, and also is able to share it with his friends across the world. Also, an enterprise storage, because it allows companies to focus on the target of their business rather than have to maintain clusters and pay people for maintaining such clusters of computers. However, the problem is security. So far in the traditional computing model, we have our data on our own computers, or enterprises. Yes?
Could you speak up?
Okay, I'll speak closer to. Is this better? Okay. So in the traditional compute model, people store the data on their own personal computers, and thus they're the only one responsible for taking care of the confidentiality of the data, of the integrity, correctness of the data, and the same for enterprises storing the data on personal clusters. However, by moving the data in the cloud is now the one who can read the data and thus can control the confidentiality of the data, can modify the data, it can return stale data to the user by not placing certain updates, or it can discard writes. And this can be a problem because there are bugs or misconfiguration in any software. There can be disk failures, or cloud employees can be careless, they can be curious, or they can be intentionally malicious. And also criminals or hackers can get access to any computer. So the problem is that right now, cloud services do not guarantee security. They only guarantee availability. So for example, if we look at the Windows Azure Service Level Agreement, for computing, the user will have external connectivity at least 99.95% of the time, and they also guarantee for storage correctness of requests at least 99.9% of the time. And they don't mention anything about security. Similarly, in the Amazon S3 Service Level Agreement, they claim that the service will be available at least 99.9% of the time, and for the cases when it's not, they reimburse the client using their so-called service credit. However, because there's no security guarantees, clients with sensitive data will refuse to place their data on the cloud. Numerous clients have expressed concerns. For example, this is a concern regarding Windows Azure, in which a user says that it's more dangerous than you think. They say that what the purpose of Microsoft is to control the data and to have unfettered access to the data, to read it, to find out about the business model of the various people, about the customers, to change it, and so forth. Also, similarly about Amazon, Amazon confirms openly that their service is not PCI Level 1 compliant. And they recommend not to store credit card information because they do not provide any security guarantees. Therefore, our goals is to enhance a service level agreement with security guarantees such as confidentiality, integrity, freshness, and Write-serializability. So basically, confidentiality is clear. It means that no one else besides the users that the customer allows should be able to read the data. Integrity means that the data in the cloud should be some version of the data placed by the user and not some junk data that the cloud put or some bug caused. Freshness means that any read to the data on the cloud returns the data from the latest update. And write-serializability means that any update to the data on the cloud is performed on the latest update. Okay, so of course we'd like this to be efficient and scalable, especially if we look at the enterprise case, which has a lot of data, a lot of users, a lot of access control groups, and so forth. So we have two main contributions. We provide the security mechanisms needed to enhance a service level agreement with security guarantees. We also design, build, and evaluate the first end-to-end secure and practical storage system. Okay, so I motivated our work. Now I will go on and present related work, our model, security protocols, and how we do access control. So there are two kinds of related work. There are cloud services, and there's research on secure file systems and data store. So in the case of cloud services, there's Windows Azure and Amazon S3, for example. But as I mentioned, they don't offer any guarantees regarding integrity, freshness, or write-serializability. There's another cloud service, Tahoe, which is a peer-to-peer cloud service, which attempts to provide more security guarantees. And in this case, the users can check whether their integrity is violated. However, they can detect this, but they cannot prove this, because there can always be a case in which a client falsely claims that the cloud changed their data when that didn't happen. Also, this service doesn't have a financial contract, so if indeed the cloud, because it's peer-to-peer, so indeed if the cloud changes the data of the client, no one will pay the client back for damages. Also, this system doesn't provide freshness and write-serializability. The second part of the related work is in secure file systems and data store, which is an extensive literature and contains systems such as Sirius, Sunder, Plotus, and so forth. So how are we different? Well, first, besides the fact that we can detect cloud misbehavior, we can prove it. Also, the cloud can disprove false client accusations. So why do we do this? Well, because in our case, the cloud is a liable entity, and there's a financial contract between the client and the cloud. The client pays for service, and the cloud pays back for damages. We also provide all of confidentiality, integrity, freshness, and write-serializability, and we are highly scalable. So how come we manage to provide all of the four when most related work only provides the first two? Well, we envision the enterprise scenario in which there is an enterprise and multiple clients, and the enterprise is trusted by the clients and can perform some minimal checking. In the case of these previous systems, they were just independent users having some access to a remote server and not talking to each other. So in our model, there are three parties: cloud, an enterprise, and many clients. The cloud is not trusted for the reasons that I mentioned before. It can change the data, it can return stale data, it can leak the data, and so forth. The clients are trusted to do whatever they want with the data they have access to, because they're allowed to change it. But they may attempt to access data outside of their access control and outside of their permissions, and they are not trusted not to do this. Also, they may try to collude with the cloud to achieve this goal. The enterprise is trusted to perform membership updates because they are the employees of the enterprise. Also, the clients and the enterprise together are not trusted to not falsely accuse the cloud of changing the data. Okay, so a service level agreement with security would sound like this. If the enterprise or the user pays a certain amount of money, then the cloud guarantees integrity, freshness, write-serializability with a certain percentage. If the cloud does not meet this, then he has to pay a certain amount of money. So note that we don't mention confidentiality here because this is entirely controlled by the clients by just putting encrypted data in the cloud. So now that for this to make sense, yes?
Encrypted data in the clouds doesn't let snoopers know what's in the data, but they can still look at access patterns.
Yes.
What the military calls traffic analysis.
Yes, I agree with that. We don't prevent against that. Yes.
So, since you're doing this like an SLA, I mean, downtime is well understood as a percentage because it's inaccessible. You're saying that some of the times the cloud can violate Write-serializability and the client, and that's okay with the client? The client would pay
no.
70% of the time you'd have Write-serializability?
No. What happens is that the way it says, so when the cloud does not meet this, they agree to pay a certain large amount of money. So basically, whenever the client can prove...
Is the percent 100% of the time?
Maybe I didn't phrase it properly. So what I mean is the cloud says, okay, if you pay this much amount of money, 99% of the time you'll have all of the security guarantees. When you don't have it, I'll pay you this much back. If you pay a bit more, then I'll give you more.
99% says that occasionally you can violate it, and that's within the SLA.
What I mean here is that when you violate it, the cloud has to pay back damages.
That would be an SLA of 100%.
Sure, in the way you phrase it.
Is it easy for the client to verify if the serializability is a guarantee, or is a break is violated? Is it
Yes.
easy to verify?
So we'll get at all of this. I will explain how everything is verified. But the bottom line is that there is some auditing going on at the enterprise. That's offline, that's lightweight, and it's easy to check in that auditing. I will explain. It's quite fast. Anyway, so in order to be able to have such an SLA, in order for such an SLA to make sense, the customers need to be able to detect and prove cloud misbehavior. Also, the cloud would not provide service if clients can falsely accuse him of damages and then get money from the cloud. Therefore, the cloud needs to have a way to be able to disprove invalid client accusations. So our solution is based on signed receipts. So at a high level, and then I will explain in more detail, the clients and the cloud exchange receipts every time the client makes a request. By the receipt, when the cloud returns a receipt to the client, it means that the cloud agrees to perform the update that the client requested, or that the cloud states that the response to a read is correct. When a client gives a receipt for a write to the cloud, it means that the client says that, yes, I allow this cloud to make this verification, make this change. Okay, so the design principle of our work is to offload as much of the work as possible on the cloud, but verify. So these are the operations that should be performed in our system. So there's read-write operations. There's integrity, freshness, and Write-serializability checks. There's access control of the users. There's key distribution needed for access control, confidentiality, and membership updates. And in fact, we managed to offload most of the work for the first 4 to the cloud, which are the most expensive ones, as I will explain. The clients are the ones performing confidentiality by only uploading encrypted data. And the enterprise only gets to do membership updates, client revocation, or client granting permissions, and some lightweight auditing to verify that the cloud has properly performed the first 4 tasks. As we'll see, both tasks are done offline, and in particular, auditing can be outsourced maybe to a second cloud or to a cluster, and we'll see it's lightweight. And both are inexpensive, as I will argue. Yes?
Membership in what?
So I said the enterprise has employees, the clients, and some employees are given access to a particular amount of data, and some are not. So membership in the sense that who are the members allowed to access the data?
So this is authorization.
Access control, yeah.
But access control is out there as a third.
Yes, access control in the sense that only certain clients can access the data on the cloud or not. And by membership here, I mean which are those clients that can do that. So the cloud makes sure that whether this client is valid or not, it can access the data, but then which are the enterprises to maintain that.
So if client data are all encrypted, why do we need the access control?
Well, you need access control because some clients should not be allowed to read it.
And if they visit?
Yes, but some
Writing.
clients should be allowed.
You need it for writing.
Yes. Well, you both need it for both. So for read, so if a client has read access, he should be able to get the key and he should be able to decrypt. If a client doesn't have read access, he should not be able to get the key and decrypt. And for write access, the same. Should not be able to write if he doesn't have access.
I guess the question is who stores these keys? The cloud stores the keys? This is sort of...
I will get at all of this. This is just high level. I'm illustrating how our design point is into the system. Okay, I'll get to all of this. Okay, so first, confidentiality. So as has been done in many previous work, each block is encrypted with a symmetric cipher such as AES. The clients have the key, and they know the decrypted value of the block. The cloud only gets to see the encrypted block and no key, so he cannot decrypt the block. Okay, integrity. Again, this is similar to what's been done in previous work. The client now has an additional signing key that's secret, and only the clients with certain access permissions know it. Now, this key is used to sign a hash of the encrypted block, and this signature is given to the cloud. Now, the cloud needs to ensure that a client cannot make a modification to a block without providing a valid signature. This is because later, if a client wants to verify the signature and it's invalid, it's junk, it means that the cloud modified the data. The cloud won't be able to produce such a correct signature without knowing the signing key. He can verify it because he knows KP, which is the public key. Okay, so now I will present the receipts and how the receipts exchange between the clients and the cloud goes before I go into freshness and write-serializability. Okay, so when a client performs a write request, he has to provide a signed request, a signed receipt to the cloud in which he says, yes, I would like you to make this change, override the existing data and make this change. So this receipt has to contain an old hash and a new hash, basically saying I'm changing the data from this state to this new state. Now, the cloud has to respond with another receipt signed by the cloud saying, yes, I agree to move this block from this hash of the block to this new hash of the block. For read, the client doesn't provide any receipt, and the cloud has to provide a receipt in which he says, yes, this is the latest version of the file, it has this hash. So it only contains the current block hash.
In this step, in the read request, how does the cloud verify this client should be authorized to do this read request?
I will get to access control as well. So, okay, so now how do we do write-serializability? So as I mentioned, write-serializability means that a write is performed on top of the latest write. So therefore, the cloud must ensure that updates are performed in the last version of the data. The way he does it is he looks at the client receipt and sees if the old hash of the client receipt corresponds to the current hash of the block on the cloud. It means the cloud had the right version. So for example, this is a timeline showing a block which initially had the hash h1. Client A comes and reads and the hash is h1. Then client B comes and he reads the block and the hash is still h1, no one changed it. Client B comes and then he wants to write it. So he advances the hash from h1 to h2. Client A doesn't know of the change and he wants to write the block and change the hash from the previous h1, which he was aware of, to a new h2 prime. The cloud should prevent this and should inform client A that a change has been made. It's up to client A what he does. Maybe he merges the versions, maybe he overwrites it, maybe he takes the old one. But any subsequent write request that client A makes has to have the new old hash, which is h2. Yes?
Why is there a requirement for a hash? Why not use a version with leases or callbacks?
You can use a version, but that won't work for later for freshness.
So,
I will explain that. Yes.
What if the same data is written twice? Would it have the same hash?
Yeah, so if it's written twice and it's the same, you mean it's the same content?
Yeah.
Or you mean the same content?
Sure.
Well, you should, well, it turns out that it's fine if there are cycles in the hash. It will work out. Theoretically, it works out. Our auditing will work out.
I'm not so sure that it will, because can't you pretend that certain things that happened didn't happen? So let's say that it's if there's a loop and then I've gone the next step in the loop.
Yes.
You can then remove that step and make it look as if it never happened.
You can remove that step only if you're the only one updating in the loop. If there were other people in the loop as well, they will be sending, as I will explain, receipts to the enterprise for auditing. So you can't just discard those people's receipts, those people's updates. I will explain.
Okay.
Because everyone is sending receipts to the enterprise for auditing. I will explain, I will talk more about that. And the enterprise will see, hey, this receipt is nowhere. This didn't happen. And then the cloud did something wrong. I will present that. Okay, so freshness. So in freshness, we'd like to guarantee that the read to a block sees the last write. In order to guarantee freshness, we add a chained hash called CH to each cloud receipt. So the chained hash for a certain receipt is equal to a hash of the previous chain hash and concatenated with the current receipt. So the chained hashes for a certain block, they chain. Basically what happens is that the chain hash for a certain receipt contains in it information about all the previous receipt history for that block. Now the reason why this gives us freshness, and I will discuss more, intuitively the reason is that if a client comes and performs a read after a certain write, and the cloud attempts to put the read before that write, giving it stale data, then the chain receipt of the write won't chain with the read before it, because the person who did the write had already received the chain receipt a long time ago, and that cannot be changed. I'll explain in more detail. This is an intuition for now. Okay, so for example,
For later verification. For the client who's reading right now, there's no way the client can make sure this is fresh or not.
exactly, the clients won't check
So this
the chain
could be a
hashes.
problem if the teller saying, hey, how much balance this guy has? They say $100,000, and I get $100,000, I run away.
Well,
You see what I'm saying, right?
sure, but the problem is that the bank, here we are trying to prevent the cloud from being malicious. And if the cloud is malicious by saying you have a lot of money,
No, it's not malicious, it's a bug.
Yeah.
It's a bug in the cloud, and you cannot guarantee, like on read, it's a fresh, because the client cannot verify it. You see what I'm saying? Like in that scenario, like who to blame? You blame the cloud. It's a bug, it's in the 1%. Even though it's $1 million, I'm not going to pay you that.
Well then, yeah, so basically what happens, so in our system, all these security guarantees are checked at the end of the month, and they are proven that they were wrong. So if you're not fine with that, so if you're not fine with that, somebody proving it at the end of the month, you just want to know every second, then you should either decrease the auditing period and do it all the time.
No, I understand you can do it offline. I'm just saying this freshness is not in real time.
Yes, if you want it in real time, you can do it in real time. You can have the enterprise in real time checking receipts all the time. But it's more cheap to do it offline. Yes.
My question is, so when you audit it and you find a problem, how do you sort of do you have to reset all these chains again to sort of say, the bug is, it's a bug, yeah, everybody agrees, let's fix the bug. How do you sort of reset everything? Now you can,
yeah, you keep the current state.
basically all the operations.
No, you keep the current state. So basically what happened is, you realize the bug, you realize that the cloud did something bad, the cloud pays you for damages, and you keep going.
But that has to be sort of a transaction between the cloud, the enterprise, and the client. I don't have to agree that, yeah, that was a bug, and now we all start with a new fresh.
It's easy for so the enterprise is the one performing the audits and gets all the receipts. The receipts are proofs in itself, and then just the enterprise and the cloud reconcile, and the cloud pays it back for damages. Of course, if you'd like to roll back, then you should maintain additional state, like loggings. Okay, so let's see how the chain hashes work in an example. So a client comes and performs a write 1, and his receipt is for write 1, and the chain hash is just the hash of the current receipt because there's no previous chain hash. Okay, now another client comes and performs a read, and now the chain hash is a hash of the current read receipt and the previous chain hash, which was just the hash of write 1. Similarly, a third client comes and performs a write, and his chain hash now is the hash of the current write receipt and the previous chain hash. Okay. So finally, auditing. So the enterprise periodically audits each block with a certain probability. Blocks that are more sensitive and enterprise cares more for them They should have higher probabilities, or they should have a probability of 100%, which means they're consistently being checked and have full guaranteed consistency. The cloud doesn't know which blocks are going to be audited at a certain time. Okay, now for the blocks that are going to be audited, the clients send receipts back to the enterprise. Send the receipts they got from the cloud back to the enterprise. Okay, so the enterprise performs the following check. It groups the receipts for each block together. Then it tries to arrange the receipts in a sequence such that the new hash of a receipt is equal to the old hash of the following receipt. So for example, here I have 3 receipts for the same block. 2 of them are writes because they advance the hash of the block from the old one to the new one. And receipt number 3 is a read. We can see that they're chained by the value of the hashes. The new hash of the first receipt is equal to the old hash of the second receipt. The new hash of the second receipt is equal to the hash of the read receipt, the third receipt. Okay, now the enterprise has to check that all these receipts form only one chain. If they do, it means we have write-serializability. So here is why. Assume that they form multiple chains, that the chain is being forked. And there's a certain client 4 who did the write 4 and send the receipt back to the enterprise. Well, it must be the case that either client 2 or client 4 reached the enterprise first. Reached the cloud first, sent the write request first. Without loss of generality, let's assume that client 2 did the write first. Then he went from hash B to hash C, everything is fine correctly. Now client 4 comes and he wants to perform the write. Then the cloud should not have allowed client 4 to perform this write and should have informed him of the client 2's update. So here is where write-serializability was not respected.
What if it's the same write?
I mean, if it's the same write, I mean, you should still send a receipt.
No, but I mean the new hash is still C, right? So client 4 and client 2 do the same update to the data.
The cloud should still inform the client, because what client 4 did is, you don't know what work he was trying to do. He was just trying to get the state of the data and advance it, and maybe if he saw that the state of the data was C, he would have done something else. So it's, yeah, the cloud should still inform of the change. Yes?
You talk about sorting the receipts. This is a topological sort, and I think it should be named as such. And if you don't have alleged date stamps, it can get very expensive.
I agree. You should have some timestamps. You should have some version numbers. In actually my implementation, I have, because it was easier to. What also you can use is the fact that these receipts will pretty much arrive in the order in which they were generated. Of course, it's not a guarantee, but that will help with efficiency because clients will perform the writes in order.
So I'm going to rephrase my question. When you verify now, what do you verify? So between those 2 records, the one in red and the one in blue,
yes,
you verify that the new hashes are different, or do you verify that they are sort of different clients?
No, so what you verify right now, what the enterprise verifies are these receipts just one chain? If the chain forks, the cloud was bad. So the enterprise wants to see just one chain, because that means the total order on the writes. It means each update saw the previous one.
Okay.
And if it's a forking, it's bad, and write-serializability was not maintained. If there's a gap, then the enterprise will contact the cloud, say there's a gap here. Maybe some clients timed out and they didn't send me the receipt. You should have their receipts. Can you give them to me? If you don't have them, you did something bad. You just skipped the hash. Okay. So for freshness, we now look at the attached chain receipts to chained hashes to these receipts, and we make sure that they also come in sequence properly. So remember, each chained hash of a receipt was the hash of the current receipt with the previous chained hash. So they are chaining. Okay. And now the enterprise needs to check that the sequence of this chain hash is the same with the sequence of the receipts from the previous sort. And this means we have freshness. So, okay, it's clear why this means it has freshness, because it means that each write was performed the previous write. Okay, let's see what happens if the cloud attempted to provide stale data. So in this case, let's assume that the read in the third receipt, when the client 3 performs the read, the cloud attempts to give him the block with hash B as opposed to the block with hash C. Well, in this case, what would have happened is so in this case, when the enterprise checks the sequence, it must have been the case that the chained CH2 chains with CH3, that CH2 comes after CH3. However, when client 2 performed write 2, he got a chain hash and he left. Then client 3 comes and performs the read. But then the cloud cannot change the chain hash he gave to client 2 because he already left. Therefore, it's not feasible for the cloud to provide CH3 to the read such that CH2 comes properly after it, unless it finds some collisions in the hash. Okay, so post-auditing, the enterprise and the cloud can throw away the receipts. They're not needed anymore. They only keep the last receipt for each block so that any subsequent writes or reads can be made as a continuation of the current state of the system. And since there can be many blocks and we don't want the enterprise to hold a receipt for each block, then the enterprise should just compute the Merkle hash and hold the Merkle hash of the whole system. And this auditing is highly parallelizable because basically what the enterprise does is just checks one chain and parts of the audit of the sequence can be delegated to different threads. Yes?
You mentioned earlier that the enterprise only audits a proportion randomly of the blocks?
Yes, so the enterprise just audits part of the blocks. Each block is given a probability. If the enterprise wants to make sure that a certain block is always correct, it will always audit it.
Let's say I'm a client and I complain a week or two later. The enterprise has already done the audits that occurred in that time period and thrown out the data. What happens then?
So you mean you complain about the previous auditing period?
Yeah.
And you complain about the block that was not audited?
Exactly.
Well, too bad for you.
It's like at the store. You only have one month to return the item. If you haven't returned it yet, it's too bad. Keep it.
Yes, because basically if you want to make sure that your update went through, you have to send a receipt to the enterprise.
Okay. You have to send a receipt to the enterprise.
Yes, if you absolutely...
That doesn't mean the enterprise checks.
Well, sure, but you can, if that block is to be audited,
so
and you want to write...
speaking, how long is an audit period?
You can make it 1 month, you can make it 1 day. It just depends on how much computation enterprise is willing to get to dedicate, how much the enterprise cares about the data. But basically, for the blocks that are audited within the audit period, it's guaranteed, we have full security guaranteed for the clients that care about the request and send back the receipts. If the enterprise really cares about some data, it can always audit the blocks. Yes?
So, will you tell us how expensive it is to audit receipts?
Yes, I will tell you. Okay. So now how do we do access control? And for this, I'd like to present 2 cryptographic primitives first that we are going to use. The first one is key rolling, introduced by Kevin Fu in 2005. So basically what happens is you start with an initial key, and from that key you can derive subsequent generations of the keys. So his tool ensures that only a party having a secret key can roll these keys forward. In our case, the enterprise. So only the enterprise will be able to roll the keys forward. Anyone can roll a key backward if they have a certain generation of the key. So for example, if someone has key at generation 3, it can generate key at generation 2 and key at generation 1. Okay, so the second one is broadcast encryption, which there have been various methods proposed. One of them is by Bonnet in 2006. So the idea is that the enterprise can encrypt a message for a group of clients. And any person, any client in that group can decrypt the message, but no one else outside of it. And there are different schemes with various complexities, but I will not get into that. Okay, so for access control, we introduced the notion of a data group, which is basically a group of blocks with identical access control lists. Now, each data group has one file in which there's key information, the file is stored on the cloud. So here's what the file contains. It contains a broadcast encryption of the current generation of the key we used to encrypt the block. So, for example, here the key is a generation I, and key I is the key that is used to encrypt all the blocks in the data group. It's a symmetric key. Now also, it contains, as I mentioned, for integrity, we use a signing key that is secret to the cloud, and the public key used to verify that the cloud knows. So now we have a broadcast encrypted version of the signing key. So now only clients who have write permissions can decrypt this broadcast encryption. And anyone can see the public key, including the cloud, and he uses it to verify integrity. Yes?
Can you change the group?
Can you change that?
The group. Can you add new members to the group?
The enterprise can add new members to the group. So basically what happens when enterprise adds new members to the group, it changes this file. It picks a new key, or maybe keeps the same one, and broadcast encrypts it for everyone now.
But do the old clients need to get this new key now to be able to decrypt it?
They will only get the keys when they go at the block, as I will explain. Okay. When they go to, okay, I'll explain it. Yes.
Confused. Previously you said that KP belongs to the client, and the client keeps it, and everything in the cloud is encrypted with KP. Now KP sits in plain text in the cloud.
So.
And that seems to be a contradiction. Not even
so the cloud has KP. The cloud knows the public key because he uses it to verify that clients are given correct form blocks, so that later the cloud is not accused of the fact that he changed the blocks. Because if ever a client comes and says, can you give me the block and give me the signature attached to it, and sees a bogus signature, it's going to accuse the cloud, because the cloud may try to change the block. And
so KP is a public key?
The KP is a public key. And is used to sign the receipt, yes. And KS and K are known only to the clients who should have access to them. Yeah, so basically the enterprise here will encrypt KI using broadcast encryption directly to only the clients who have read access. So only those clients will be able to decrypt the broadcast encryption. And the same for the signing key, the secret key, is only the clients who have write access will be able to decrypt the broadcast, because the broadcast encryption was generated just for those. And this file is protected, is read-only to the clients, and it's read-write to the enterprise. So basically, it's checked using the mechanisms I described, but it's audited all the time, for example. Okay, so how do we do revocation? Well, when a member leaves a data group, the enterprise needs only to change the data group file. The enterprise won't go and encrypt all the other blocks with the new key. So basically, it selects a new signing key and the new public key, and it encrypts the signing key with the new membership that has write access control. Then it rolls forward a new generation of the confidentiality key used to encrypt the blocks, and again encrypts it only, broadcast encrypts it only for those clients that still have read permissions to it. Now we have a lazy revocation. We have a lazy revocation approach in which basically the enterprise doesn't go and encrypt all the blocks to which the revoked client had access to. We instead just guarantee that any further changes won't be seen by the client. And basically what happens is when clients come to check the file, clients that still have access permissions to the file, they will re-encrypt the file with the new key. Yes?
When you re-encrypt the file, you have to erase the old encryption, right? The encryption, the blocks encrypted with the old key.
Yes.
So if the member that you want to revoke the key for colludes with the cloud, yes, you're screwed.
So as we say, we adopt lazy revocation that we just prevent against future changes to the files not to be seen to the client, to the revoked client. And the rationale for that is, well, first, efficiency, and second is that well, if a client had access to the blocks, he could have downloaded them before.
No, but sure, just to understand, I'm not saying. Just,
Yeah.
Okay.
Sorry. And I mean, of course, if you want to make sure, you can just spend more computation cycles and have the enterprise re-encrypt them.
Well, you have to trust the cloud that the cloud erases that old encrypted data,
Yes,
right?
and you can't trust that.
And you can't, yeah. So it's sort of, yeah, okay, fine. I mean, it's hard.
Okay.
But
No.
so
Yes.
that's like in practice, usually when you leave the company, they don't want you to see the data anymore. Even though you may download something, but doesn't mean you still there's maybe have a huge amount of data. I mean, you didn't download beforehand before you are laid off or fired. Then you still can access all the data, even though 1 year later, that sounds not so meet the practical requirements.
I mean, I agree. And we can't trust the cloud to erase it. We can't check that. Later on, if you somehow determine by some other means that the client still had a copy of it, then you just, sue the client.
It's a trade-off, right? It's a trade-off because you use this this row key, right? Because you want to have this backward compatible so that then anyone ever have access to those files and they can decrypt it, right? That's the trade-off you have.
Well, I think the trade-off comes in place by the fact that we store it on the cloud, because the cloud can always keep old versions of the data, and we can't stop him from doing that.
So just the problem between a trust model of maliciousness and a trust model of bugs. You're paying an SLA,
Exactly.
and if you suddenly assume there's maliciousness, well then things like persistence can't be guaranteed.
Yes.
I mean, one operator could take bribes to drop the latest version of your file, and Amazon's happy to pay you $1,000 when you've lost your billion-dollar project.
Yes.
I just tacking on the maliciousness aspect to the cloud just seems like there are these other guarantees that you want
Yes.
that you might not be able to provide ever.
Yes, and I agree with the fact that we don't necessarily think of a cloud that's intentionally malicious, because the cloud would go out of business really soon.
I can argue that.
But anyways, if the cloud is absolutely intently malicious, he wants to be bad, it's the company's goal, then yeah, persistent data we can prevent against that. The cloud can just make a copy, and a user who used to have access to it can still have access to it. And that's, I think, inherent in storing outside of your clusters. Okay. So the receipt, as I mentioned, the receipts serve to prove cloud misbehavior or disprove invalid client claims, as I discussed. However, there's a problem because these receipts need to be exchanged in an all or nothing fashion. Here's why. So assume that a client wants to make a write and he gives the cloud a receipt. The cloud times out and he doesn't send the cloud receipt back to the client. Then the cloud has the write receipt from the client, and he can choose to apply the change or not. Whatever he chooses, he's backed up because he has the proof that the client requested that change. Also, if we go the other way around, in which the cloud sends the write receipt first, and then the client needs to send it after, and the client says, oh, I timed out, I didn't send it, then the client has the cloud receipt, and he can accuse the cloud. So for example, if the cloud doesn't know what to do because he didn't get the client receipt, he can either apply the data or not. If he doesn't apply the data, then the client can accuse him saying, hey, he gave me this receipt, he said he agreed he will apply it. But if the cloud does apply the data, does apply the change, then the client can accuse him saying, I never asked him to make this change. He doesn't have a receipt from me, so I never asked him. Therefore, these receipts need to be exchanged in an all or nothing fashion. And there are cryptographic primitives for this, like fair exchange by Micali in 2006. The problem with this one is that it invokes a trusted party whenever a problem occurs, when one of the parties doesn't send the receipt. And that's not very efficient because it can happen that clients time out. So we adopt a change solution, which is in which the cloud does send the receipt first, then it waits for the client to answer. If the client doesn't answer, the cloud contacts the enterprise saying, can you please annul his write request?
Sorry, whose write request?
So if a client sends a write request, then the cloud sends back the receipt, but he doesn't get the receipt from the client. He waits for a while, and if he doesn't get it, he goes to enterprise and annuls it. Okay, so I presented our protocols. Now I will go on present the implementation, evaluation, and then I will conclude. So I implemented the system in about 5,000 lines of C# just for our code. Of course, this runs on top of some Azure storage client and also uses some other external code. So the way Azure works, I don't know how many of you are familiar, is it has two kinds of roles. It has web roles, which can contact and which can talk to outside parties over the internet, and work roles which don't have access to the internet. The web roles don't scale. I think the limit right now is 2 web roles. I mean, definitely it's 2. I don't know if they're going to scale it. But the purpose of the worker role is for scalability, and they can be a large number of worker roles can be deployed. Currently, it's still 2. Because Azure is in early stages. There are some tokens that allow you to have 25, but they don't fully work always. But anyways, soon they will be able to deploy much more worker roles. Then there is a storage, which is in the form of blobs, queues, and tables. We are only going to use blobs and queues here. And the means of communication between the web role and the worker role is through storage. Okay, so here is how a typical write request, let's say, would work in our system. So the client performs an HTTP request to the web role. The page loads, and the web role places this request in a queue on which the workers are waiting. Now a worker picks up the request from the queue, does some processing. Maybe he gets some blobs from storage. And then once he's done and has the result, he places it in a blob, in an answer blob, on which the web roles are waiting. So basically, each web role tells the client in which blob to put the result. Once the web role got the result back, it sends it back to the client. So the storage and the web roles are not necessarily stored in the same data center. Okay, so here is, for example, the average read latency for the no security, for the just confidentiality, and the full security case. We can see that for no security, it's 0.6 seconds. It's kind of high. However, we'll see that throughput is good. And it's kind of high because storage and worker roles are not necessarily collocated, and there's all these round-trip times between client, worker roles, storage, and so forth. Maybe in future releases, it's going to be more efficient. For confidentiality, which is the lightest form of security people usually have nowadays, it's slightly higher. And for full security, it's about 0.1 seconds above confidentiality. And this is not necessarily because of the cryptography, but it's more because of the fact that the client receipts are each stored in a blob, so that the cloud backs up the receipts he gets from the clients in case the enterprise asks him for. So he stores them in a blob. I could improve performance by batching multiple receipts and storing them in the same blob, because every access to the blob storage takes some time. Yes?
Does blob size affect the performance?
In read and write?
No, I mean like if encryption, decryption, right? If you have to do something either on the client side or on the server side, probably not server side. On the client side, I have to encrypt a huge file. If your blob is huge, then it certainly will increase the latency. If it's very small, it will decrease latency.
I agree.
But on the other hand, if the blob is too small, then you have way too many receipts.
That's true. What we do is we just have a typical 4K blob store. And it's true that for a larger blob, the overhead of crypto, like just one receipt, and it's much smaller, and it's actually, I think, more. It's actually saving efficiency, because throughput, as we'll see, is good. Just latency is slightly too much because of all these round trips. So for writes, with no security, we have 0.7 seconds, and with full security, we have 1.1 seconds. This is again because we store more receipts in that case, and I will try to look into like batching them and not accessing blob storage so often. Yes.
This is assuming no contention.
This is write latency. So yeah, it's assuming no contention. This is just one client doing 100 writes and checking the average.
Serially. Okay.
Yeah. But they're not batched, like one after the other. When one finishes, starts the other one.
And each write is 4K?
Yeah, 4K. Yes.
Does this include the time to encrypt the block at the client?
Includes. Includes in the confidentiality and full security, not in no security, because there is no such thing, no encryption. Okay, so for throughput, this is a large file, 20 megabytes is sent. And so we can see that for no security, it's about 4.4 megabytes per second throughput. Confidentiality is slightly less, and full security is also slightly less, about 4 megabytes per second, so the difference is not that high. Write throughput is lower, and that's because of writing blobs is lower. So we can see that no security is about 370 kilobytes per second, and with full security about 340 kilobytes per second. So basically the bottom line is that adding the security to our system doesn't incur much costs according to the baseline. I mean, based compared to the baseline.
On the other hand, it's just like your network pipe to the cloud storage is so narrow. You see what I'm saying? It's only without anything you only achieve 300.
Yes, but Azure is just. I mean, I'm sure they're going to improve it. It's like in very early stages, and it's not even billing right now.
Do you agree, like, if the network pipe is so narrow, when you see your difference is very small, it doesn't say much?
He wants you to redo this experiment and you only look at the server. Don't take the client.
I see.
Not only that.
No.
Oh, because you
basically,
think
I mean, I just want to say that the latency give us a lot of information, but throughput,
I agree.
when the narrow pipe is
agree.
very narrow, I see, oh, the difference is really small. That doesn't say much.
But for no security and confidentiality, you don't actually write. Your write could just be you don't actually have to do these serially because you're just writing data, so you could send it all at once and get rid of all that latency and have a true throughput number. With these, are you waiting for the response before you do the next write?
So this is just one large file write.
So
It's sent all at once.
it's sent all at once, so it's been going into.
It takes.
Okay, so there's all the blocks get written in parallel, basically.
So what happens at the blob storage level? I mean, what I do is I do. No, they're written sequentially. Yeah.
Is this a test bed that you created, or is this the actual?
I created. I mean, I use my storage system and I send one big file, and I put it into storage. Yeah.
Is it storage locally or remotely?
Remotely.
I mean,
On
in
the cloud,
data
yes.
centers.
Yes.
Did you measure CPU utilization? Traditionally, for performance, we don't care, but modern data center servers, green, energy, air conditioning, power consumption, blah, we care.
So I didn't really measure it, but later I have some results in which I have multiple threads on the same worker. And since they are quite parallel, I would say that there isn't that much high CPU utilization.
That doesn't make any sense.
Yeah, I didn't measure. I will look into it, yeah.
Just doing straight unencrypted reads and writes isn't going to touch the CPU much at all. It's just taking the data and shoving it to disk. Encryption is going to impose a lot more CPU overhead.
Yes, I did not look explicitly into that. Yeah, I will look into that. But anyways, here is, so basically what this wants to say is that if the block size is larger, you can have better performance. Because I write this file all at once in one blob. So I don't split it in blocks and then write them separately. Anyways, so this shows the scaling the number of workers. As I mentioned, unfortunately, I could only get 2 workers because Azure currently does the limit for a user account. However, I try to have like 2, 4, 3, 4 threads per each worker. And I measured the number of requests per second as increasing number of workers, and we can see that even though I only got to about 8 threads, it looks like it scales linearly. So auditing performance. So this graph shows the running time as depending on the number of receipts. This is just one thread going through the chain of receipts, trying to audit them. And I put the axis in logarithmic on both sides because the numbers were getting too large, and you would only see the 1 point. Yes.
It's interesting to see audit overhead as a fraction of the overhead to actually do the writing. So if you're consuming X resources a month, what's the fraction of X that your audit is consuming? Do you have any intuition for that?
I don't think it's that high because for one blob auditing, so let's say two consequent writes to one blob is in the order of microseconds. So I think, so for example, 100 million receipts are going to take 4 minutes to audit in one thread. And I'm assuming that maybe one block will only have about 1,000 changes in a month. Or maybe let's say 10,000 or 100,000. And that still would be, I don't know, about 10 seconds to audit that blob in a month. So I don't think it's a significant amount. But yeah, it's an interesting experiment to run.
Do you get a receipt on reads?
You get a receipt on read, yes. Anyway, so I also looked at parallelizing auditing, and I didn't produce a graph, but it looks linear, and we'll put it in a subsequent paper. So.
Why wouldn't it be linear? I mean, do you have any intuition?
Why wouldn't?
What? Yeah.
I mean, there's still some setup. Among the threads, yeah, it's linear. It's proof of concept.
You have those receipts, you check something, you check next receipt, you do something, why it should be linear, right? The more you see them, it should more look like a linear.
Yes, and it's linear, but it's a proof of concept maybe.
Yes.
I mean, I guess there's still some, part that just one person does, and that separates in chunks for different threads, and then the threads go on and audited. Okay, so. In conclusion, we provide a security-enhanced SLA, and we provide a novel secure cloud storage system that provides confidentiality, integrity, Write-serializability, and freshness, and it's scalable to the enterprise size. We are also looking on search, but I did not include it here because it was too much material. Thank you. Yes.
I have a question. If you list the multiple properties, do you have an intuition which one has more cost in terms of performance that you would drop? I mean, if you pick one to drop, which one would you drop to save performance?
Well, Write-serializability and freshness kind of happen together because they need the receipts. So if you drop the two, then you don't have the receipts, and you don't have the auditing anymore either. So confidentiality and integrity are the easiest to achieve. But the problem then is that you don't have fresh writes, and fresh reads and writes. So yeah, the most expensive are the last two. I think they're about the same because you need the receipts and.
So this tool applies to unstructured data stored in the clouds. But what about for structured data in Azure SQL? Do you think they can use your tool or not?
To extract the data from...
Yeah, to protect the structured data in Azure SQL database.
So you can protect individual files.
Or Azure DB service.
I mean, you can protect the file in which the table is stored, but some connection between various files, consistency between various files, we don't have that because we treat the files independently. And just because we treat the files independently, we allow concurrent updates, which gives us scalability. If you want them to be, together, if you want them to be consistent with each other, then you should treat them basically like one file in terms of receipts. All receipts for the two blocks need to be serialized. So that's the change you need to do. As opposed of having just one chain of receipts for each block, you should have one chain of receipts for the two correlated blocks together. So, yes.
I need a concrete model if the cloud is Microsoft Azure, and the client is Joe the plumber. Who's the enterprise?
Okay, so what happens is, so we look at the enterprise like a startup company. So the enterprise is the startup company, like a bunch of servers on the
So
enterprise.
what are the clients then?
The employees.
Employees.
So this targets that this I mean the aim, one of our main goals is scalability for huge companies who'd like to store their data in there, and they have a lot of employees and they need scalable access control and yeah.
The client is Joe the plumber.
The clients, the startup's customers.
The enterprise is his employer.
Sure, they can be startup customers, they can be startup employees.
Startup employees like two of them. Most startup employees, the number of startups.
Sure, then
most startup number
sure,
of
then the
businesses.
customers as well. Then the customers as well. But anyway, if you would like to apply this to the personal storage case, you can. And the enterprise is the owner, and the people with whom he shares the file are the employees, the clients here. Or the social network, friends.